Hi students, we are at topic 18 on carboxylic acids and derivatives. So I hope before you begin this particular chapter, you have done some revision on the earlier organic chemistry topics. I don't want to sound like a recorder, but it is important for you to get a good foundations in the earlier topics before you move on to the last two organic chemistry topics. Okay, so maybe to reiterate a little bit, you have learned 5 mechanisms in total, which are the requirements for H2. So in JC1, you learned about free radical substitutions. Okay, so that is pertaining to the alkane functional groups. Okay, so basically you need the UV light to generate the reactive chlorine bromine radical in order to force a reaction out of the sp3 hybridized CH bond so as to activate it towards free radical substitution. Okay, then later on in alkenes, you learn about electrophilic addition. So for electrophilic addition, the focus is on the electron-rich pi bond attacking the electron deficient electrophile. Okay, then right before promotional exam, you learn about electrophilic substitution. So that is related to arenes. Okay, so I hope you have remembered all these, and you have just taken your consolidation test on arenes, solubility, product, and acid-base equilibrium. So I think electrophilic substitution shouldn't be too far away. It shouldn't be too unknown for you. Okay, then this year you learn 2 additional mechanisms. Okay, so you learn about nucleophilic substitution. That is for halogen derivatives. Okay, or sometimes we call it Rx. Yeah, so you react a compound with the carbon bonded to a halogen. So usually the carbon is a sp3 hybridized carbon. So the nucleophile will be electron rich, so it will replace the halogens. Otherwise we call the leaving group. And then the last topic, topic 17, you learn about nucleophilic addition. Okay, so the difference between electrophilic addition and nucleophilic addition I have emphasized quite a bit in the topic on in the earlier topic. So I've mentioned that the reason why nucleophilic addition occurs for carbonyl compounds is because the carbonyl carbon is electron deficient and therefore susceptible to nucleophilic attack. Yeah, so most of the electron density in ketones or aldehyde is displaced towards the oxygen, so that makes the carbonyl carbon highly vulnerable to nucleophilic attack. But in the case of alkenes, the pi electron cloud is evenly distributed between the two sp2 hybridized carbon. Yeah, so it will likely to repel away the incoming nucleophile. Okay, then that's when we stopped, and then we're going to move on to this particular topic on carboxylic acid derivatives. Those of you who have taken H3, you have learned this a little bit earlier. Yeah, because in H3 I think we covered a mechanism known as addition elimination. Yeah, and topic 17 is also a topic where I briefly mentioned about addition elimination. Yeah, so more about that, we'll deal with that later on. Okay, so there are several learning objectives you need to be familiar with. So under your syllabus document is 11.7. Yeah, so if you read through everything, you'll notice that first of all, you are required to describe the formation of carboxylic acids from alcohols, aldehydes, and nitriles. You have learned them in the earlier topics, right? So for alcohols, that will be topic 16, where you can oxidize a primary alcohol to a carboxylic acid. Okay. In the topic on aldehydes and ketones, you learn that if you oxidize aldehydes, it will go to the carboxylic acid. Okay, so for primary alcohol, the first product you get is usually aldehydes. If you are not using a very strong oxidizing agent such as potassium dichromate, and then if you heat it under reflux, it will go all the way to carboxylic acid. Okay, so you already learned about learning objective 11.7a. Okay, and then of course for nitrile, I think I emphasized that in the topic on halogen derivatives. I mentioned that for nitrile you can simply do acidic hydrolysis. after you replace the halogen with Cn, right? So learning objective 11.7a is not something too distant away. Okay, so for objective 11.7b, you are required to describe the reaction of carboxylic acid in the formation of salts. So basically this is an acid-base neutralization reaction. Yeah, so you subject carboxylic acid to, say, sodium hydroxide, and then you get the sodium carboxylate salts. Yeah, so that's not very inspiring because you have learned that in secondary school. And then the next one is on esters, on condensation with alcohols. So using ethyl ethanoic as an example, you learned that in secondary school as well. So basically, if I have ethanoic acid and ethanol, if I catalyze the reaction using corn sulfuric acid, I will be able to get ethyl ethanoic as the ester. So ethyl ethanoic is known as a carboxylic acid derivatives. Yep. Something new for H2 will be acyl chloride. So you might have heard me mention that acyl chloride is a more reactive version of ethanoic acid. Yeah, so if you want to use a milder condition to form the ester, then acyl chloride will be preferred rather than carboxylic acid. Okay, so we'll deal with that when we reach the relevant section later on. Okay, primary alcohol. We can obtain primary alcohol from carboxylic acid simply by reduction using lithium aluminium hydride in dry ether. Okay, so this is very important. And then of course we need to use ethanol as an example. So we're going to reduce ethanoic acid using lithium aluminium hydride dry ether, and then our final products will be ethanol. Okay, so it seems that you're quite familiar with some of these topics as I go through with you the learning objective. And this is also a way in which you should be revising for your organic chem. Yeah, go through the learning objective and be honest with yourself. Ask yourself whether you are able to explain or describe some of the things required of you. Okay, so next we're going to look at 11.7c. You're supposed to explain the acidity of carboxylic acid and chlorine substituted ethanoic acid in terms of their structure. Yeah, so what are they trying to say? Basically, they are trying to say that if I attach an inductively withdrawing group such as chlorine, right, it will enhance the acidity of ethanoic acid or carboxylic acid in general. It's not something that is very surprising because you learn from an earlier topic, acid-base equilibrium, that any factor that helps to stabilize the conjugate base of an acid will enhance the ionization of the relevant acid. So in that sense, any inductive withdrawing group or electron withdrawing group via resonance effect, or if you are able to allow the negative charge to be delocalized into the pi system, etc., right, it will help to enhance the acidity of the system. So it's not something that is new. Okay, of course, we'll discuss more about that when we reach the relevant sections. Okay, so 11.7d, describe the hydrolysis of acyl chlorides. Again, acyl chloride, when you hydrolyze it, you will get the carboxylic acids, and that also explains why acyl chloride is the reaction involving acyl chloride has been done under dry condition. Okay, so reaction needs, or rather, this actually tells you that whenever I want to use acyl chloride to react with something, provided it's not hydrolysis reaction, then I need to keep the condition dry, because any presence or any hints of the presence of water will actually hydrolyze the acyl chloride. Yeah, so in that case, the amount of acyl chloride present in the system will be reduced drastically. Then for objective 11.7e, supposed to describe the condensation reaction of acyl chloride with alcohols, phenols, and primary amines. So we're going to talk about it later on. Yeah, so acyl chloride, being the more reactive version of carboxylic acids, is able to react with alcohols, even phenols, and even primary amines. Yeah, you might want to take note that for amines, right? Amines does not react with carboxylic acid directly. So if you react amines with carboxylic acid, they will form the carboxylate salts and the ammonium salts, the ammonium carboxylate salts in general. Yeah, you will not be able to obtain the amides. So in order to get the amides, you need to use acyl chlorides. Okay, then next for 11.7f, explain the relative ease of hydrolysis. Okay, so this is a very important learning objective, the ease of hydrolysis of acyl chloride, alkyl chloride, and aryl chloride. Yeah, you have learned about alkyl chloride and aryl chloride in the chapter under halogen derivatives. So for 11.7F, we have an added section on acyl chloride, which is very important because amongst all three, acyl chloride is the most reactive. Okay, then 11.7G describe the formation of esters from condensation reaction of acyl chlorides using phenol benzoate as an example. Yeah, so if I'm going to draw phenol benzoate, it will look like that. Okay, so there's an O here. Okay, so this is phenol benzoate. Okay, so in order to get phenol benzoate, later on you will realize that I can use an acyl chloride, that's benzoyl chloride, and of course phenoxide, being the more reactive version of phenol. Yeah, using phenol works as well, but maybe it will take a longer time for the reaction to take place. Okay, so this is a condensation reaction, so chloride will be the byproduct. And then finally for 11.7H, I'm supposed to describe the acid and basic hydrolysis of esters. So this is just description. Yeah, it's not like in H3 where you have to draw the mechanism of the hydrolysis. So there's a bit of a difference here. So do not be confused with what you are going to learn in H3. Okay, yeah, so with that, I'm going to move on to the first section. My apologies, it takes a bit of time for me to give you the introduction earlier on because I thought that I just want to introduce a way of revision for your organic chemistry by going through the various learning objectives. Okay, so for the first section, introduction to carboxylic acid. So again, they are trying to describe to you the geometry around the carbonyl carbons or about the carbonyl carbons, 120 degrees. If you are stricter, we don't call that the carbonyl carbon, it should be called the carboxyl carbon. But carbonyl carbon works as well because after all, the RCO group is what we call the acyl group. Okay, so this is known as the acyl moiety. Okay, so this is called acyl. Yep, and then these are some examples of carboxylic acids. Methanoic acids is on the left. Okay, so first isolated 17th century. Ethanoic acid, otherwise known as acetic acid, so very important. This is your vinegar. Okay, and then citric acid is found in citrus fruits and flavorings. And then of course there are the rest of the carboxylic acid. Some of them is part of omega-3 Okay, so and then of course a painkiller, which is aspirin. Okay, so if you wish to, you can go ahead and read about the did you know. If not, then I'm going to just move on to the nomenclature. Okay, so for nomenclature, straight chain carboxylic acid are named, okay, so again by replacing the terminal E with the corresponding Oic acid. So if you recall from what we talked about in introductory organic chemistry, for methane, that's for one carbon. Yep, CH4. So if we want the carboxylic acid equivalents, that would be methanoic acid. Yep. And then for 4 carbons, 1, 2, 3, 4, that will be butanoic acids. Okay, but in our case here, we are looking at alkene, so we are looking at butanoic acid. If you want to give the geometry, then it will be cis-butanoic acid. So maybe a better representation will be something like this. Yeah, for cis-butanoic acids. Why is this a better representation? Because it allows you to see the trigonal planar geometry about the sp2 hybridized carbon. Okay, which is part of the CC double bond. Okay, and then of course you have the rest, 2 propyl pentanoic acids. Yeah, so why is it called 2 propyl pentanoic acids? Because the longest chain contains 5 carbon over here. Okay, of course this is 5 carbon, so 1, 2, 3, 4, 5. The other way around is also 5 carbon. If I want to name it this way, it's also okay. Yeah, so doesn't really matter. So 5 carbon. Second carbon is the one with the side chain, which is the N propyl side chain over here. So this is the N propyl side chain. Yeah, so we call it 2 propyl propanoic acids. Yeah, what is probably a little bit more common will be substituted carboxylic acids or halogen substituted carboxylic acids, such as 2-chloropropanoic acid, like the one given over here. Yeah, so the carboxyl carbon will take the priority 1. Okay, so if you count from the carboxyl carbon all the way, then that will take 1, and then the next carbon, which is the alpha carbon, will take on numbering of 2. Yep. And then the next sections, compounds containing carboxylic acid group bonded to a ring, named using the suffix carboxylic acids. Okay, so what are we trying to say? So for example, this particular compound clearly is a 5-membered ring. Okay, so it's a 5-membered ring over here. So a 5-membered ring, as you learned, is called cyclopentene. Yeah, but in our case here, the first carbon where the carboxylic acid is bonded to, right? It's also where the double bond is present. So in this case, we have to distinguish it. We have to call it a cyclopent 1-in, and then that's a carboxylic acid. So it's cyclopent 1-in carboxylic acid. Okay, then the next compound over here. So in the ring structure, there's a total of 6 carbons. So that will be a cyclohexane. Okay, and then we need to indicate the position of the relevant substituent. So at the second position, you have the hydroxyl group. Okay, and then at the 5th position, you have the methyl group. So in this case, we call it 2-hydroxy 5-methyl cyclohexane carboxylic acid. Yeah, then I think the rest are straightforward. So for example, I have nitrobenzoic acids. As you know, this is known as benzoic acids. Yeah, and then if you just go down the ring, the 4th position or the power position is substituted with the nitro group. Yeah, so we call it 4-nitrobenzoic acid. And then in our case here, this is known as a benzene. Yeah, so 1st position and 2nd position both are bonded to a carboxylic acid, so we call it benzene 1,2-dicarboxylic acid. Yeah, if you find the naming a little bit confusing, then I think it's actually okay, because as I said to you, even in the earliest chapter, the naming is not the main emphasis for H2 Chem. Of course, it's good to know how to name simple structures. Yeah, but most importantly, you need to be able to recognize the structure from the name. Yeah, which is why we have example or exercise 1.1 over here. So for exercise 1.1, you are required to draw the structural formula for each of the following compounds. So let us do it step by step. Okay, so number 1, we have butanoic acid. So again, butanoic acid has 4 carbons. Okay, like this. Okay, so the next thing we want to do is to number the carbon. So that would be carbon 1, 2, 3, 4. Okay, then we are aware that carbon number 3 has the methyl group over here, and then carbon number 2 has the hydroxy group. Yep, so this will be the structural formula for 2-hydroxy 3-methyl butanoic acids. Yeah, so remember to always identify the parent. That is extremely important. Right, okay, then next, something a little bit more complicated. Okay, so we have something known as a cyclohept 4-in. Okay, so definitely is a 7-membered ring. So I'm going to draw out a 7-membered ring first. Okay, like this. Okay, some students have difficulty drawing 7-membered ring, so maybe I can teach you how to draw it. I think I mentioned it in the earlier chapter, but if you forget, you can follow what I'm doing now. So we all can draw 6-membered ring because it's symmetrical hexagon like this. Okay, 7-membered ring, what you need to do is to expand this a little bit. So you tilt the vertical line to the left a little bit, and then this you tilt to the right a little bit. Okay, so when you draw it out, it will look like this. A little bit to the left, a little bit to the right. Okay, then the rest you just follow, but you leave a space in the middle for you to draw the horizontal line. Okay, so like this. Yeah, so this is the way to draw the 7-membered ring. Yeah, it doesn't really matter where we draw the CC double bond. Okay, so I just choose one position like this. Okay, but what is more important is in terms of the numbering. So remember that the alkene numbering, right? The 4th one is the lowest number. So 4. So after that, I'm going to just go one round. 5, 6, 7. I'm not going to go 8, 9, 10. I'm going to go back to 1, 2, 3. Why is that the case? Because we are saying that the CC double bond is present in the 4th position, and then the 1st position is a carboxylic acid. Okay, so I can just draw a carboxylic acid functional group out, and then the 3rd position is another carboxylic acid functional group. Okay, so what I'm drawing here will be cyclohepta 4-in 1,3-dicarboxylic acid. Yeah, so this is how I'm going to draw out the compound from the name. Okay, so I hope it's not too difficult for you. Then yeah, if everything's fine, we're going to move on to the next section, section 2 on physical properties. Yeah, so again, every organic functional groups, we will talk about the physical properties. Sometimes it gets a bit boring, I understand, because most of you will think that you have learned them in the earlier chapters, chemical bonding. Yeah, but it does help if you can go through it a little bit, so as to assimilate yourself with like the similarity or differences in terms of boiling point with compounds having the same number of carbons lah. So for I mean, just to give you a very simple example, so in our case here we have ethanol, okay, and then the MR is 46, and then we have methanoic acids, the MR is 46 as well. You notice that methanoic acid, the boiling point is higher than ethanol, which is 101. Ethanol is actually 78. Yeah, and then we go down the group, we have propane 1-ol, 60 MR, boiling point 97 degrees Celsius, and then for ethanoic acid, that's 118. Yeah, so if they have the same number of electron clouds based on the MR, then usually the carboxylic acid will have a higher boiling point. The reason, again, it's relatively straightforward. Yeah, so I think we have listed it down in the notes. Yeah, it's the presence of the electron withdrawing CO group. So the delta plus on the H gets intensified, and the OH group is more polarized. Okay, and sometimes you also expect a more extensive hydrogen bonding between the two carboxylic acids. Yeah, it's more extensive because I have more hydrogen bonding sites. Like for example, for carboxylic acids, I think it's shown over here. You not only do you have two lone pairs here, this is one lone pair, then potentially there's also another two lone pairs over here. Yeah, despite the fact that I only have one protonic hydrogen, yeah, but occasionally the hydrogen bonds can be a little bit more extensive. Again, this is due to the greater delta plus which is being imposed upon the H. Yeah. And then in our case here, I'm expecting the hydrogen bonding to be stronger. Okay, dimerization is also possible, especially in pure liquid state lah. So when we have dimerization taking place, then you are expecting two strong hydrogen bonds to be bonded on both ends lah, like the one given in the figure below. Okay, then solubility. So again, due to the carboxylic acid functional group having hydrogen bonding sites and hydrogen donating sites, hydrogen bonds donating sites, then I'm going to expect some extensiveness in the hydrogen bonds where the carboxylic acid functional group can forms with water molecules. Yeah, but in water molecules, you realize there's a slight difference. The water molecules will be able to form stronger and perhaps more extensive hydrogen bonds with carboxylic acid. Yeah, so the dimerization of carboxylic acid will cease to exist in water molecules if it is sufficiently diluted. Yep, okay, so I think we show you how to draw the hydrogen bonding over here. So that's something which you probably want to focus on when you draw hydrogen bonding, and make sure you label your hydrogen bonding. Yeah. Very often in exams, the students do not label properly. Okay, but if my carboxylic acid hydrocarbon chain gets longer, the solubility in water will actually decrease. The reason is the dispersion forces formed between the non-polar chain becomes stronger and stronger. Yeah, so because they become stronger and stronger, the energy released over here. Okay, sorry. Okay, so energy released from the formation of hydrogen bonds between the carboxyl group and the water become less exothermic, so it doesn't release enough energy to overcome the dispersion forces between the non-polar group and at the same time existing hydrogen bonds between the water molecules. Okay, so because of that, if my hydrocarbon chain or the non-polar chain gets longer, you will expect the solubility of carboxylic acid to reduce. Yeah, and in our case here, benzoic acid is very, very insoluble. It's only slightly soluble in cold water, but dissolve readily in hot water. And I think you can also understand why, because when the system becomes more energetic, then the probability of forming hydrogen bonds actually gets increased because of an increase in randomness and kinetic energy of the solvent as well as the organic molecules in question. Okay, yeah, then with that, I think we can discuss exercise 2.1. Which of the following statements best explains why the boiling point of propanoic acid is higher than that of 2-fluorobutane? So we're asking you boiling point propanoic acid higher than 2-fluorobutane. Okay, so over here, the relative molecular mass of propanoic acid is higher than that of 2-fluorobutane. If you try to calculate, you realize they are about the same. Yeah, so this is definitely not the reason. Covalent bond is stronger. This is of course nonsense, because when we are boiling, we are not overcoming intramolecular bonding. In this case, we are not overcoming covalent bonding. Yeah. The third reasoning seems to make a little bit more sense. Hydrogen bonds between propanoic acid molecules, okay, exist. Okay, but between 2-fluorobutane molecules, probably we're expecting some form of permanent dipole interaction or dispersion forces. Yeah, so the hydrogen bonds between propanoic acid molecules is definitely stronger, so therefore I need more energy to overcome them. Yeah, which leads to a higher boiling point. Okay, then propanoic acid has a larger surface area than 2-fluorobutane. Of course, this is nonsense as well. Yeah, so it doesn't focus on what the question wants, because for a boiling point, if both molecules or both covalent compounds clearly have different intermolecular forces of attractions, we need to focus on discussing the intermolecular forces of attractions. Yeah, of course, the focus here, the assumption here is that they have similar MR lah. If they have different MR, then really there is no point in even discussing intermolecular forces of attractions, because when the size of the electron cloud gets significantly larger, the instantaneous dipole-induced dipole interaction, or what we call dispersion forces, become stronger and more significant. Yeah, so definitely it leads to a higher boiling point. Okay, so with that, we are done with 2.1. Next, we're going to deal with the preparation of carboxylic acid, which, if you notice what I did earlier on, I have gone through with you some of the preparation. Okay, so now I will go through with you the 7 bullet points over here. So oxidative cleavage of alkenes, right? So in particular, for the oxidative cleavage of alkenes, we are looking at alkenes having at least one hydrogen bonded to the sp2 hybridized carbon. Yeah, because if the two groups here are R groups, then I'm not going to get carboxylic acid, I'm going to get ketone. Yeah, so one of the group must be a hydrogen, so that when I perform oxidative cleavage, eventually it will lead to the formation of carboxylic acid. Okay, side chain oxidation, this is quite limited, because we can only get benzoic acids, or rather we can only get a carboxylic acid functional group directly bonded to the phenol ring. Okay, then acid and alkaline hydrolysis of nitriles, we discussed extensively in the topic on halogen derivatives, so I will not go into it. Oxidation of primary alcohol, we talk about that as well. Oxidation of aldehydes, we talk about that as well. Okay, so both of this, we use potassium dichromate heat under reflux. Okay, hydrolysis of acyl chloride we'll discuss later on in section 6.2.1, and then acidic and alkaline hydrolysis of esters amides, we'll cover that in the later topics. Okay, especially for amides, we'll deal with that in the next topic on nitrogen compounds. Okay, so without further ado, I think it does make sense if we just jump straight into the question. So for exercise 3.1, question number 1, suggest the product form from the oxidation of 2-methyl 1-butanol using hot acidified potassium permanganate. Okay, so first of all, we need to draw this structure out. So again, we are actually looking at 1-butanol. So 2, 3, 4. Okay, so the first position has an OH. Okay, and then of course the second position is a methyl group. So if I'm going, so this is a primary alcohol, obviously, because carbon number 1 is where the OH group is bonded to. Yeah, so if I subject it to KMnO4, acidified with H2SO4 and heat, okay, I expect to get a carboxylic acid. Okay, because a primary alcohol will be oxidized all the way to a carboxylic acid in the presence of acidified KMnO4. Okay, then for question 2, the same carboxylic acid is obtained either by the hydrolysis of a nitrile, which is P, or by the oxidation of an alcohol Q. Which of the following pair could P and Q be? Okay, so we have to be very careful, yeah, because for P and Q, both of them must contain the same number of carbons. Yeah, I think that is very important. The same number of carbon. Yeah, straight away, if you count the carbon and they are different, you know that they can't be the answer. So, for example, option A, we have this particular nitrile with 3 carbon, and then we look at Q, that it only contains 2 carbon. Yeah, so if the the carbon count is wrong, so therefore A cannot be the answer. Okay, if you look at B, do a quick count in the number of carbon. So I'm going to have 4 carbons on the left, and then for Q, 4 carbon as well. But you notice that Q is actually a tertiary alcohol. Yeah, so as you might have remembered earlier on, a tertiary alcohol do not undergo further oxidation. Right? Okay, so B is out as well. Okay, then if we move on to C, it's a little bit difficult to see, so I'm going to just draw it out. So this is a phenol ring. Okay, bonded to a chiral carbon, and then this chiral carbon is bonded to a methyl group and then a CN. Okay, so when this CN gets hydrolyzed, I'm going to end up with a primary alcohol. Yeah, but for this, if I'm going to sketch it out, right, you realize that it might look a little bit different. So it's like this, yeah. So when I oxidize Q, I'm going to get a ketone. Yeah, so definitely Q will not lead us to the same carboxylic acid as C. Okay, so therefore I'm crossing both out. Yeah, for donkey, what I'm going to have here is just like this. Okay, and then I have a CH2 and a carboxylic acid functional group over here. Okay, then of course for Q, you notice that this CH2 essentially corresponds to this CH2. Okay, so if I'm a little bit strict, yeah, I'm going to look at this CH2 and this CH2. Yeah, so that means that for Q, we are also dealing with a primary alcohol. And remember that when you perform oxidation here, you cannot use potassium permanganate, because potassium permanganate will cause Q to go all the way to benzoic acid. So do not use potassium permanganate. So you need to strike it off. In our case here, I'm going to use potassium dichromate acidified with H2SO4. Yeah, because side chain oxidation is not possible in the presence of potassium dichromate. So I can safely use it to oxidize the primary alcohol all the way to the carboxylic acid. Yeah. And B, option E, if you look at the carbon count, is incorrect. 7 carbons on the left, 6 carbon on the right. So definitely I will not choose E. Yeah, so my final answer is D. Oh, sorry, not D. Yes, D. Yeah, okay, so D will give us the same carboxylic acid upon hydrolysis as well as oxidation. Okay, yeah. Then finally, we have a slightly more complicated synthesis question for carboxylic acid derivatives. Supposed to give the synthetic rocks to show the conversion of the halogenal alkane to propanoic acid. Okay, so I need to convert all to propanoic acids. Okay, so I think first of all, propanoic acid has 3 carbon. In our case here, there's only 2 carbon. So of course, what you can imagine will be, first I need to add in an extra carbon. So I will do that by using ethanoic KCN. Okay, and then I need to heat it under reflux. Heat under reflux to ensure the reaction goes to completion. And then in the process, I'm going to end up with the cyanide group replacing the Br. Yeah, and then if I want to perform a hydrolysis, I will simply just add H2SO4. Okay, and then heat. Yeah, and then this is known as acidic hydrolysis. So eventually I'm going to get propanoic acid. Okay, yeah. For part 2 is a little bit different because the carbon count is correct. So 3 carbon on the left, 3 carbon on the right as well. So I'm definitely not going to do a substitution reaction, but what I can do is I will need to be able to oxidize this particular bromopropane into its corresponding alcohols, and then eventually carboxylic acids. Yeah, so in this case, first I need to convert it to the alcohol. Okay, so I'm going to get the alcohol. How do I convert it to the alcohol? What you have learned in nucleophilic substitution, sodium hydroxide heats. Okay, so I'm going to get the alcohol, and then from the alcohol I'm going to perform oxidation. You can either choose potassium dichromate or potassium permanganate, it doesn't really matter. Okay, so eventually I'm going to end up with the carboxylic acids, right? Okay, and then the final bits, you have a compound with more carbon than is required. Okay, but not to worry. If I'm going to sketch this out, you'll know where the hint is. So this is a Br, okay, and then a CH2, CH2, CH3. Yep. What we can do is we can first perform a dehalohydrogenation, or what we call an elimination reaction. Okay, using ethanoic KOH. Okay, and then heat. Yeah, heat under reflux, or you can just put heat. Okay, so eventually I'm going to get the CC double bond over here, and once I get the CC double bond over here, because this is like an elimination reaction, I can technically perform oxidative cleavage to obtain the carboxylic acid functional group. Yeah, so for oxidative cleavage, CmO4 equals H2SO4 equals, and then I will heat. Okay, and then I think there's one part I didn't draw the H. My apologies. Yeah. Okay, so I'm going to heat, and then oxidative cleavage will occur. So when oxidative cleavage occurs, then I'm going to get two equivalent of propanoic acids. Okay, would that be alright? I hope it's not too daunting, not too tough. Okay, so I mean, if we are done with this, we can move on to section 4, which focuses on the reactions of carboxylic acids. The LOs have already been listed here, and I've gone through parts of it with you, so we'll just go straight, okay, into the characteristics of chemical reactions involving carboxylic acids. Okay, so there are three kinds of reactions we are looking at. So first of all, we are looking at the acid-metal reaction, or acid-base neutralization reaction. So if I'm going to sketch the H out from here, okay, so I'm just going to sketch the H out. Okay, just a sigma bond to a H. Okay, this is what we call the protonic hydrogen. So the protonic hydrogen will undergo acid-metal and acid-base reaction. Yeah, and in the process, you will generate a carboxylate salt. Yeah, so this is quite common if say we have a good base, or a metal where it can potentially donate its electron to it, and in the process forms hydrogen gas. Yeah, so the acid-metal reaction is redox in nature. Acid-base is not redox. Acid-base is simply just a neutralization reaction. Very often students get confused between the two. Okay, but what is most important, right, is nucleophilic acyl substitution, or sometimes we call it addition elimination. Yeah, so basically for the acyl substitution reaction, the OH group is being replaced. Yeah, so this group is being replaced. It's sort of being made into a leaving group, but the OH does not just leave like this, so it goes through a complex series of reactions. Yeah, so for example, in the formation of ester, the OH group is being replaced by OR. So this is in the formation of ester. Yeah, in the formation of amides, the OH group is being replaced by H2 and HR or NHR2. Yeah, so it's either or. Okay, either of this, depending on whether you're using ammonia, primary amine, or secondary amine, etc. Okay, sorry, it's not NHR2. I think I shouldn't be writing NHR2. It should be NR2. Okay, yeah. And then for the whole group, which also involve the carbonyl carbon, or the carboxyl carbon for that matters, right? We can also perform a reduction. So when the carboxylic acid is being reduced, I'm going to end up with a primary alcohol. Okay, so essentially the reduction involves introducing hydride equivalent, or H-. Okay, so in this case, I think this is a pretty important statement. The CO and OH are so close, so carboxylic acid do not behave like alcohols, ketones, or aldehydes. Yeah, so they behave more like acids, strong acids, because the negative charge on the conjugate base, O minus, can be delocalized into the CO group or the carbonyl group. Okay. Carboxylic acid do not undergo nucleophilic addition like ketones and aldehydes. For a very simple reason, due to the presence of OH. So any potential nucleophilic addition reaction, right, might result in the decomposition of the products. And I think over here we give you an electronic reasoning. That is, the delocalization of electrons makes the carbonyl carbon less electron deficient. Yeah, so less susceptible to nucleophilic attack. And at the same time, if you look at 2,4-dinitrophenolhydrazine, if you look at the structure, it is basic at the nitrogen site. So if you forget the structure of 2,4-dinitrophenolhydrazine, basically it's a phenol ring bonded to NH and then NH2, and then this position is NO2 and then NO2. Okay, so I'll focus in the NH2, so maybe I write it out more clearly. So NH2. So the NH2 has a lone pair of electrons, and the hydrazine behaves like a base. So together with carboxylic acid, it might undergo acid-base neutralization reaction. Okay, so therefore, it's not so easy for 2,4-dinitrophenolhydrazine to undergo the kind of reaction you expect for ketones and aldehydes. Okay, so this is a very important LOs on the acidity of carboxylic acids. Okay, they are weak Bronsted acid, but definitely stronger acid than phenol and alcohols. For a very simple reason, because for the conjugate base being formed, the negative charge can be delocalized into the carboxyl group, or you can call it the C double bond O group. Okay, and if you want an orbital appreciation, so basically we are looking at RC. Okay, and this is the CO double bond presence. So this is the CO double bond presence. Okay, and then I have an O minus here with a negative charge. Okay, so one of the lone pairs electrons is parallel, so it can delocalize into the CO pi system. Yeah. So this delocalization, some of you who are doing H3, it will be represented by the drawing of this particular resonance structure. So the lone pairs of electrons delocalize into the CO pi bond. So we call the carbonyl oxygen the electron sink, and the lone pairs of electrons on the O minus the electron source. So when you push electron density from the source to the sink, you will end up with something like this: O minus and then double bond O. Yeah, so delocalization of lone pairs of electrons on the negative charge onto the carbonyl oxygen can be represented by this particular resonance structures, these two resonance structures, by showing the relevant arrow pushing. If the drawing of resonance structures is not something which you are very comfortable with, then an orbital diagram like this will suffice in your explanation. Okay, but in short, whatever representation you use, the main focus is in the dispersal of the negative charge. Okay, so the more dispersed the negative charge, the less likely it will be able to accept a proton. Yeah, so if we have an inductively withdrawing group at the R, so let's say it's a Cl bonded to maybe one of the CH2s there, then it will be able to inductively withdraw electron density away from the carboxylic anion, further reducing the electron densities at the carboxylic group. Yeah, so making it a stronger acid. Okay, yeah. Then we'll take a look at this relative acidity of carboxylic acid, phenol, aliphatic alcohols. Yeah, so in general, if you heard me from the if you hear me and remember what I said in the tutorials, it will be good for you to remember some basic pK values. I think these are good values to remember. So alcohols, we can just call it remember it at 16, maybe water about 15.7, phenol about 10, ethanoic acid around 5. Okay, so if you remember these three values, it will help a lot in your explanation and maybe in the arrangement of the acid and acid strength of carboxylic acids. Okay, yeah, so I think we mentioned over this, we mentioned this above, the negative charge delocalized equally over two highly electronegative oxygen. Why is it equally? So I think the main question is, in this case, why is it equally? It is equally because the structure is symmetrical. Okay, and there is no difference in whether the negative charge is on one oxygen or the other. So you can call it so in the end, the average value is probably half negative charge on both ends. Yeah, so this is the resonance hybrid that is preferred. Yeah, but usually it's not being drawn in real life because it is difficult to draw mechanism based on a resonance hybrid. Yeah, so whenever chemists showcase resonance structures like this, we do understand that the two Lewis structure on the left and right, they do not adequately represent the structure of carboxylates. Okay, what can adequately represent the structure of carboxylate will be something like this. Okay, then perhaps you might also want to remember from earlier portion that the negative charge on phenoxide is also delocalized over the phenol ring, but why is phenol less acidic than say carboxylic acids? Yeah, because some students really get confused, because if you look at the phenoxide anion, the negative charge seems to be delocalized over 7 atoms, okay, as compared to the carboxylic anion, which is simply over 3 atoms. But not to forget, for carboxylic anion, the negative charge is spread out equally between 2 oxygens, which are highly electronegative. Yeah, but for phenoxide, carbon being less electronegative than oxygen, you do not expect the delocalization to be of any huge significance. So generally we say that the negative charge on the O- in phenoxide is simply just partially delocalized into the phenol ring. Yeah, so this partial delocalization is obviously not as good or not as effective as compared to that of a carboxylate anion. Right? Okay, yeah, so and then of course for alcohols, electron donating group intensify the negative charge on the alcohol side. Yeah, so destabilize it, so make it more able to abstract back the H, plus it donates away to water. Okay, yeah, so the difference in the acid strength of carboxylic acid and alcohols can be easily distinguished by using sodium hydroxide as well as sodium carbonate, and of course sodium in this case. Yeah. Do take note that for sodium we are looking at redox reaction between a metal and three kinds of protonic hydrogens. One in aliphatic alcohols, the other one phenols and carboxylic acids. Yeah. So it's essentially a redox reaction, and in the process generates hydrogen gas. So remember, this is redox, and hydrogen gas is generated along the way. So H2 is being released. Okay, for a strong base such as sodium hydroxide, okay, so we are looking at acid-base neutralization reaction. So very weak acids such as aliphatic alcohols will not be able to react with sodium hydroxide. Okay, so that's why it's crossed out here. Okay, phenol and carboxylic acid, as you have learned, will be able to react with sodium hydroxide. Okay, so for sodium carbonate, being a relatively weak base, it's not able to react with phenol. Yeah, but for carboxylic acid, it's a strong enough acid to react with sodium carbonate. Yeah, so when sodium carbonate reacts with carboxylic acid, in the process, it will generate effervescence of CO2. Okay, yeah. Okay, so I think this table is quite important, and I think in the earlier portion, I think the in-class exercise for alcohols, we do teach you how to explain some of these things. We teach you something like why is it that the carbonate can react with carboxylic acid but not with phenol. I think we explain to you based on the fact that we give you additional information such as the pKa of carbonic acids, which is about 7 point something. Yeah, so when sodium carbonate react with carboxylic acid, it will generate carbonic acid before CO2 is being given off. Carbonic acid is a weaker acid than carboxylic acid. Yeah, so that's okay. Yeah, but when sodium carbonate reacts with phenol, it will generate carbonic acid, which is a stronger acid than phenol. So therefore, the reaction is not likely to take place. Okay, so generally, when two species react, they will have to generate a weaker equivalence in the product rather than a stronger equivalence. When I say equivalence, that means it should be generating a weaker acid and base rather than a stronger acid and base as compared to the starting materials. Okay, yeah. I think what I've said is being illustrated over here. So this is from topic 14 under acid base equilibrium. Yep. I think earlier on in the very beginning, I think 2 minutes ago, I was talking about this, the reaction between ethanoic acid and bicarbonate, okay, which is a stronger base than ethanoate. Okay, and then moving on to phenol. As I mentioned earlier on as well, phenol is a weaker acid as compared to carbonic acid. Okay, and of course, what about alcohols? Alcohols are weaker acid as compared to water, so they do not undergo acid base neutralization reaction as shown above, so it doesn't react. Yeah, so these two are being crossed out. Yeah, so do take note of them as you do your revision. Yeah, so in general, this idea of two species reacting via acid base to form a weaker version of themselves, it usually works. Yeah, because when we say that the forward doesn't work, that also tells you that the backward will be preferred. Yeah, so in that case, if I have an ethoxide and water, I will be able to generate OH minus. And some of you might remember from the tutorials or lectures I mentioned that OH minus is the stronger base which can exist in water. Yeah, and nothing else. Okay, so again, if I have a stronger base here than this, then the reaction will be reversed. Okay, so eventually I should be able to get the carbonate, okay, out. Right, and of course, for the above case, then it should be a forward reaction because I'm producing a weaker base and a weaker acid as compared to the corresponding bicarbonate and ethanoic acids. Okay, yeah. With that, I think we can move on to exercise 4.1. We are supposed to arrange the following molecules in order of decreasing acid strength. Okay, as Bronsted acids, so decreasing acid strength. Yeah, so the strongest acid will be on the left, the weakest one on the right. So I'm just going to write them out for easy referencing. So strongest acids. Okay, so this is the right hand side will be the weakest acids. Okay, then in our case here, HCl will be the strongest acids. Okay, HCl. Okay, and then this is followed by ethanoic acids. Okay, so earlier on we have already discussed about ethanoic acid. The pK is about 5. Okay, and of course this is followed by carbonic acids. I think we have already discussed carbonic acids. pK is found is given to be 6.4. Okay, so this will be carbonic acids. Yeah, carbonic acids. And then this is followed by phenol. I think phenol is something which you are familiar with from the chapter on hydroxy compounds. And then of course finally ethanol. Okay, ethanol pK is about 16. So that makes it the weakest acid of the lot. Then 4.1b states if each of the following reactions will occur. If yes, complete the equation. Okay, so I think we have done this quite several times. So phenoxide, will phenoxide be a stronger base than bicarbonate? So of course the answer is yes, because phenol is a weaker acid as compared to carbonic acid. Remember, phenol pK is about 10 from the above. Carbonic acid is about 6.4. Yeah, so this reaction will work. Okay, and then what about ethanoic reacting with carbonic acid? Is definitely no. Why? Because ethanoic acid is a stronger acid than carbonic acid. Yeah, so the reaction will go backward instead. Okay, then will ethanoate be protonated by HCl? So of course it will be protonated by HCl. Okay, why is that the case? Because ethanoic acid is a weaker acid than HCl. Yeah, okay, so the strongest acid that can occur in water is H3O+, or in this case H+. Yeah, so I'm going to expect the reaction to occur to give me chloride. Yeah, the reverse will never be able to take place because chloride is a very weak base. What about ethoxide reacting with ethanoic acid? So obviously a reaction will take place because ethoxide is a stronger base as compared to ethanoate. Okay, so ethanoate is a weaker base than ethoxide. Yeah, and ethanol is a weaker acid than ethanoic acid. Yeah, so the forward reaction will be favored. Okay, so I hope exercise 4.1 gives you a little bit of a glimpse on how to work on problems related to the acidity of acids. Okay, next we are going to look at the effects of substituents on acidity of carboxylic acids. So again, as a revision, I think in the earlier chapters I mentioned how do we look at effect of substituents by looking at whether the substituent intensify or reduce the charge of that particular center. Yeah. So in our case here, when we look at the effect of substituent on the acidity of the carboxylic acid, we need to look at whether the substituent stabilizes or destabilizes the conjugate base. When we mean destabilizes, meaning it intensifies the negative charge of at the conjugate base. Okay, so if you know that my conjugate base is generally negatively charged, so therefore electron donating group will increase the negative charge. Yeah, then electron withdrawing group will reduce the negative charge. Yeah, so therefore donating group will result in destabilizing the conjugate base, and therefore the POE or the position of equilibrium will lie more to the left. Yeah, so therefore extent of ionization decreases. So extent of ionization decreases. Yeah, then in the opposite case, the extent of ionization increases. So when the extent of ionization increases, it makes it a stronger acid. Yeah, and then the decrease in the extent of ionization makes it a weaker acid. Okay, can we see it from the pKa? So I think the answer is yes. So if we have an electron donating group in general, so let's say we have an electron donating group, methyl, ethyl, and propyl, right? You'll notice that the pK is quite similar. It's about 4.8, close to 5. But if we have a H here, which is neither donating or withdrawing, you notice that the pK reduces drastically. Yeah, so the increase, the presence of the electron donating group intensifies the negative charge of the carboxylic anion. Okay, so it will cause the position of equilibrium to lie more to the left as compared to the right. Then the withdrawing group have the opposite effect. So in this case, the electron withdrawing group tends to be a inductively withdrawing group or sigma withdrawing groups. Yeah, because resonance effects can't exactly be present, because if that is present, then it might, any severe form of effect that is present might result in decarboxylation, which I don't think we want to discuss over here. We did discuss in the earlier in-class exercise. Okay, so the stabilization of the anion helps. So if we have a hydroxyl group, the pK reduces quite drastically. So the hydroxyl group is what we call a sigma withdrawing group, or electron withdrawing via the sigma bonding framework, by virtue of the electronegativity difference between carbon and oxygen. Some of you might remember from the arenes chapter that OH group is donating, but I think I did mention to you OH group and NH2 groups are quite special. Yeah, so maybe I'm going to highlight this. Okay, these two groups, right, are what we call sigma withdrawing, okay, but pi donating. Okay, when there are two effects at play, opposite each other, right, the pi donating effect usually wins. But in our case here, right, because this is a sp3 hybridized carbon, right, the pi effect will not be present. Because for the pi effect to be present, the carbon needs to have either an empty p orbital or even a filled p orbital, so that the lone pairs of electrons can be delocalized over. Yeah, so when the lone pairs can be delocalized over, this will help to increase the electron density of the carboxylic anion. But this is not possible in our case here. Yeah, so because of that, then when we have a sp3 hybridized carbon that is flanking in between OH and the carboxylic acid group, then the pi withdrawing effect cannot be felt. So therefore only the sigma withdrawing effect, which is an inductive effect, right, will be present to explain. So in this case, it will increase the acidity of the carboxylic acid. Yeah, because the withdrawing OH group, the sigma withdrawing OH group, okay, will further disperse the negative charge at the carboxylic anion, or the further disperse the electron densities at the carboxylic anion. Okay, so the more electronegative the halogen, the greater the withdrawing effect, as can be seen here. Okay, so the lowest pK for carboxylate, for ethanoic acid is when the H is replaced by a fluorine, okay, followed by chlorine, and then bromine, and then iodine. Okay, when I increase the number of electron withdrawing group, you notice that the pK reduces drastically. Yeah, so essentially trichloroethanoic acid is a very strong acid because the pK is like 0.64. Yeah, so this is a very, very low value, low pK value. That means the Ka is quite high. Okay, yeah, so the proximity of electron withdrawing group to the carboxylic acid group is also important. Yeah, so preferably it should be at the alpha position, which is the carbon directly bonded to the carboxylic acids. Yeah, if it's shifted to the beta position, you notice that the pK value increases quite drastically. And if I shift further, then it is quite close to a normal propanoic acid or normal carboxylic acid. Yeah, so therefore, for inductive withdrawing effects, it decreases drastically with distance. Yeah, so in fact, once it's at the third position, the effect is no longer very significant. Yeah, I mean, of course, it is still significant, 4.05 versus 4.82. Yeah, but it's not as significant as when it's at the alpha position, where the inductive withdrawing effect is felt the strongest. Okay, next, before we do exercise 4.2, we can look at the effect of donating and withdrawing groups for substituted benzoic acid. I think this thing needs no further introduction. So the benchmark for benzoic acid, of course, is 4.19. Okay, so I think first of all, we need to understand why is benzoic acid a stronger acid than ethanoic acid. Okay, so I think first of all, right, a lot of students tend to be confused over, is the phenol ring donating or withdrawing? Yeah, it really depends on what it is bonded to it. Okay, so maybe I can sort of explain a little bit. Okay, so the phenol ring contains 6 p unhybridized p orbital, and then I have a carboxylic acid over here. Okay, so let's say it's a carboxylic anion, so there's a COO minus, okay, over here like this. Okay, so this delocalization is happening over the CO. Okay, now what exactly is going on here is that you notice that the negative charge when the carboxylic anion is being formed, it's what I show you over in the purple. You notice that they are next to the phenol ring. So if they are next to the phenol ring, right, you would expect part of the electron density to also overlap with the pi electron cloud of the phenol ring. Yeah, so in this case, right, compared to ethanoic acids, so let's say compared to ethanoic acids, so ethanoic acids like this with an O, and then of course an O minus. Okay, compared to ethanoic acid, right, the alkyl group is donating. Yeah, so this donating nature of the alkyl group will intensify the negative charge. Yeah, but when the p orbital overlap continuously, like what is shown in benzoates anion, right, it helps to make the negative charge less negative. So it kind of like stabilizes the carboxylic anion a little bit more. Yeah, so that is why benzoic acid has a lower pK as compared to ethanoic acid. Yeah, but if I have a donating group, it intensifies the pi electron cloud of the phenol ring. So therefore, right, the negative pi electron clouds or the negative charge on the carboxylic anion will delocalize to a slightly smaller extent. So that explains why the pK is higher. So methyl benzoic acid is a weaker acid as compared to benzoic acid. And then chlorbenzoic acid on the reverse, because it withdraws electron density away from the phenol ring, the negative charged on the carboxylic anion can delocalize to a greater extent. And then if I have a pi withdrawing group or a very strongly electron withdrawing group, okay, then the negative charge at the carboxylic anion can delocalize to a even greater extent. Yeah, so therefore, nitrobenzoic acid turns out to be a much stronger acid. In fact, it's close to 10 times stronger as compared to a normal benzoic acid. Okay, yeah. Then with that, we're supposed to arrange the compounds in order of increasing pKa values. Okay, so I'm going to draw this out. Okay, so just going to use a bit of space here. So this is high. I will just write increasing pKa values. Okay, pKa values. Okay. So I would expect ethanol to be the highest. I think we all understand that. Remember that ethanol is alcohol, so pK is about 16. Okay, so it's about 15.9, 16. And then this is followed by water. Okay, so water is here. I think water we understand, we already discussed it. Okay, and of course, phenol should be next. pK is about 10. Okay, so I think all these we understand. Maybe the difference is between ethanoic acid and chloroethanoic acid. I think we do understand that chloroethanoic acid is likely to be a stronger acid as compared to ethanoic acid. Okay, because of the inductively withdrawing chloro group, which helps to further disperse the negative charge or the electron cloud at the carboxylic anion of chloroethanoate. Yeah. So in this case, I'm going to put chloroethanoic acid here, and then this is followed by ethanoic acid. Okay, so I think exercise 4.2 is pretty straightforward. We won't discuss too much. Okay, and then of course next is acid metal or acid base reaction, which I think we have discussed earlier on. So acid metal reaction is redox. Okay, do take note that you get half H2. So if you want one equivalent of hydrogen gas, I will need 2 equivalent of ethanoic acid and 2 equivalent of sodium. Okay, so do take note of that. Yeah. Then the rest are acid-base neutralization reaction, which are definitely not very inspiring. So you do get CO2 along the way. So effervescence can be observed, but sometimes it can be a little bit slow. Okay, so it's not very brisk. Yeah, it can be slow depending on temperature as well and the strength of the carboxylic acid. 4.2, we are looking at a mechanism known as nucleophilic acyl substitution, but can I emphasize that this is not in your H2 curriculum, so not in H2 syllabus. Yeah, if you are ever required to draw the mechanism, then you'll be guided how to draw it. Okay, so for example, usually they will say something like, first, a nucleophilic addition takes place at the carbonyl carbon, and then after that, this is followed by eliminating the leaving group X. Yeah, something along those lines. Yeah, so I won't go into details because we have a box here trying to explain to you what nucleophilic acyl substitution is. Okay, so you might just want to cancel this plus. I think this should be a delta minus delta plus over here. Yeah, so the nucleophile attack, pi bond breaks. Okay, and then after that, this is a nucleophilic addition step. Okay, so this is an addition step. Okay, and then after that, you reform the pi bond, you kick out the leaving group. So this is the elimination step. Okay, so sometimes nucleophilic acyl substitution is also known as addition-elimination mechanism. Yeah, but do take note that I think I emphasized this in some of the H3 lectures. Nucleophilic acyl substitution mechanism does not always happen this way. Yeah, along the way, there needs to be some modification to the mechanism. Okay, so for example, the carbonyl oxygen tends to be protonated. Okay, and then or sometimes the leaving group needs to be protonated in order to make it a good leaving group. Yeah, so what is being shown over here, right, is just a very generic mechanism. So what do I mean by a very generic mechanism? So that means that what we have shown here is just a mechanism which show you the two key steps, addition step and the elimination step. It doesn't represent all reactions, all nucleophilic acyl substitution happening in this manner. It doesn't happen that way. Okay, so I hope you do recognize that and don't just draw the mechanism blindly. Yeah. So for example, if you are going to react acyl chloride, or rather you're going to react carboxylic acid with, let's say, PCl5 to give you acyl chloride. Yeah, it doesn't just happen like that. Okay, I think it needs at least 6-7 steps to complete the mechanism. It's not just 2 steps. Yeah. So a little bit of modification is required. Okay, yeah. So without further ado, I think I'll just move on to this part. Condensation to form esters. So the reaction with carboxylic acid and alcohols to give you esters. Condensation usually releases H2O as a small molecule. Okay. Phenol cannot. Yeah. The reason why phenol cannot it's because for the nucleophilic acyl substitution, or in this particular condensation reaction, right, the nature of the alcohol is important. So the more nucleophilic the oxygen is, the faster the reaction. So meaning that alcohols has 2 lone pairs on the oxygen. Okay, so you know that R group is usually electron donating, right? Yeah, so the electron donating R group intensify the electron density at the lone pair. Yeah, so the better the lone pairs, the more readily the electron density is available on the lone pairs, the faster will be the nucleophilic acyl substitution or the condensation reaction. But in the case of phenol, the lone pairs of electrons delocalizes into the phenol ring. Yeah, so it makes phenol less nucleophilic as compared to an alcohol. Yeah, and this is maybe a little bit out of the curriculum, but in condensation reaction, the CO bond is broken instead of the OH bond. Okay, so that means when we have a carboxylic acid over here, yeah, it has already been determined that in the course of reaction, right, the OH group gets replaced and not the H. Okay, because the reason why this needs to be mentioned, right, is because for an alcohol, there are actually 2 ways you can get H2O out. Okay, so one way is like that. Okay, maybe I use a different color ink. Orange, this is one way. Yeah, this is the correct way. So that means that the OH is replaced by RO group. Yeah, so another way which things can happen is like this. Yeah, so therefore what it means is that H is replaced by R. Yeah, but it has been proven that the light blue one is incorrect. Okay, so it's incorrect. Yeah, what is correct is the one I circled in orange. Okay, yeah, it's being proven by isotopic labeling under reaction mechanism, but we won't go into details at this stage. If you're interested, you can maybe find out a little bit more from other sources. Okay, formation of acyl chlorides. Okay, so like alcohols, the OH group in carboxylic acid can be replaced by Cl from thionyl chloride. So from various reagents, you can use various chlorinating reagents such as thionyl chloride, phosphorus pentachloride, or phosphorus trichloride. Okay, so usually we will use PCl5. Easier to remember, it's solid. So observation will be white fumes of HCl being released, and in the course of reaction, I'm going to generate the acyl chlorides. Okay, so acyl chloride is this particular function group with a C-double-O and then a Cl. Yep, and then you need to remember the byproduct POCl3. Okay, how to remember it? Basically, in the course of the reaction, the oxidation state does not change for phosphorus, remains as +5. Yeah. Okay, so in order for it to remain as +5, it needs to have a doubly bonded oxygen and then the remaining group as Cl. And then, of course, the remaining 2 Cl, one of them is directly bonded to the acyl carbon or the carbonyl carbon. The other one is being given off as HCl. Okay, yep, and then PCl5 works as well. 3 equivalent of it gives you H3PO3, which is a weak acid. Okay, yeah, so just going to move on to the next part. Thionyl chloride works as well, but thionyl chloride produces 2 gases, HCl and SO2. Yeah, so the SO2 needs to be removed, and usually when we conduct reaction like this, which give off gaseous molecules, right, we will usually bubble the gas into sodium hydroxide. Yeah, so that the acidic gas do not pollute the environment. Or, I mean, if you don't care about the environment, then your reaction vessel, will be corroded quite easily when acidic gas is given off. Okay, so we can easily convert carboxylic acid to acyl chloride, and acyl chloride is very, very reactive. They are usually the more reactive version of carboxylic acid. Yeah, so that is why any other kind of derivatives from carboxylic acid, we call them carboxylic acid derivatives. Yeah, because they can make to react like carboxylic acid, but whether they are more reactive or less reactive really depends on what kind of functional group you are talking about. Okay, I think we mentioned this. Carboxylic acid can be reduced to primary alcohol and only primary alcohols. I think you can understand why, because only primary alcohol can give you carboxylic acid. Okay, reagents and condition, lithium aluminum hydride in dry ether. I think I also mentioned in the earlier topic, usually in actual lab environment, right, an extra step is needed because when you react them with lithium aluminum hydride and dry ether, what is going to form is the very reactive salts or very reactive species where oxygen is bonded to aluminium. So you need to hydrolyze that particular bond. How do you hydrolyze that bond? You usually hydrolyze either by adding H2O or acid. Okay, so it has to be done in nitrogenous condition. Okay, so carboxylic acid can only be reduced to primary alcohol, not aldehydes. It's possible, in fact, to be reduced to aldehydes, but not in your syllabus. Okay, yeah. I can use a weaker reducing agent to reduce ketones, aldehydes back to alcohols, but sodium boron hydrides, okay, so, I mean a weaker reducing agent such as sodium boron hydride or H2, right, they will not reduce carboxylic acid. Yeah, so in this case, when we are able to do them or plan the experiment in a strategic way, right, if I have two functional groups, let's say a ketone and a carboxylic acid, right, I'm able to strategically reduce the ketone, okay, using sodium boron hydride and methanol. So if I use lithium aluminum hydride dry ether, then both the ketone and the carboxylic acid will be reduced. Okay, so again, you need to be a little bit strategic when you are performing such reaction. Okay, so I think when you are working on your tutorials or the in-class exercise, then you will encounter some of these reactions more. Okay, so there's a special case, but I wouldn't call it a special case because we have already explained in the earlier chapter. So I think if you want to, you can skip this portion. If not, then you can just hear me out in the next 2 to 3 minutes. There are two carboxylic acid that can undergo further oxidation, methanoic acid and ethanedioic acid. This is especially the case for the reaction with KMnO4 and only KMnO4. I've explained in the alkenes chapter, because your CH bond is being activated by the carbonyl group. Yeah, the activation of the CH bond by the carbonyl group, right, will cause the electron density between the C and the H, okay, to be quite energetic, okay, and they can easily be removed if I put a strong oxidizing agent next to it. So the electron density can easily be donated to a strong oxidizing agent such as the manganese in KMnO4, which has an oxidation state of +7 at the manganese center. Yeah, so because of that, when you subject methanoic acid to KMnO4, an oxygen will be inserted between your H and the carbonyl carbon. So what you are going to get is the first product you are getting is carbonic acid like this. Okay, and you know that carbonic acid is not stable, so it will quickly decompose to give you CO2 and H2O. Yeah, the CO2 it can be seen over here, and then the remaining portion will be the H2O 1, 2, 3. Okay, and then you heat it under reflux. Yeah, and that's how you get your two products. Ethanedioic acid I have also explained to you guys in the chapter on alkenes. Yeah, the main thing is I have two highly electron withdrawing CO group, and this highly electron withdrawing CO group weakens the CC bond drastically. So in a similar case as methanoic acid, the CC bond is activated, so the sigma electron density can easily be donated to the +7 oxidation state, or the manganese center in permanganate, which is very desperate for electron densities. Yeah, so because of that, eventually I'm going to end up with CO2, and you can easily find out where the CO2 where can the CO2 comes from. Okay, so but I will not go into details. Okay, yep. So with that, we have exercise 4.3 and 4.4. Okay, so for exercise 4.3, we have compound P used as antiseptic cream. P can be oxidized from the lab from compound Q by a method which involves intermediate R. Okay, and draw the structure of intermediate R. Okay, so you notice that the group that which remains, right, is the phenol group. I hope you do notice that. So there's no change made to the phenol group. Yeah, but you notice that there is an increase in carbons. Okay, but this is an ester. Yeah, so therefore I would expect R to be carboxylic acids. Okay, so because it is only with carboxylic acid that we can obtain an ester. And how do we obtain ester? We obtain an ester by refluxing R with potassium, not potassium, in acidified H2SO4 with methanol. Yeah, so methanol is the alcohol which gave rise to CH3 over here. So methanol acidified H2SO4, but the H2SO4 must be concentrated H2SO4, okay, in order for the reaction to take place. Okay, maybe it's a bit messy, so let me just rewrite this. So we need methanol here, okay, and we need the catalyst to be consulfuric acid, okay, and it has to be reflux. Okay, some students ask me why is there a need for consulfuric acid to be introduced? Okay, I will give you a very simple reason. May not help a lot, but yeah. Basically, a carboxylic acid, right? The carbonyl-carbon is not very, it is electron deficient, but it is not sufficiently electron deficient to be attacked by a weak nucleophile such as methanol. So the role of consulfuric acid, right, is to protonate the carbonyl oxygen. So when it's protonated, right, there's a plus charge here. It makes the carbonyl-carbon more electron deficient. So when the carbonyl-carbon is more electron deficient, a weak nucleophile such as methanol can then perform a nucleophilic attack on it, and then the pi bond will break. Yeah, if you are interested in this, you can either read up more or you can ask your H3 friends to explain to you on how the reaction actually works. But if not, then I think it is sufficient to know that the purpose of consulfuric acid is to protonate the carbonyl oxygen in order to make the carbonyl-carbon more electron deficient, so that it is more susceptible to nucleophilic attack by a weak nucleophile such as methanol. Okay, and the reagents that is needed for step 1, I think it's quite obvious. We are going to perform section oxidation. So therefore, what we're going to do is KMnO4, acidify with H2SO4, and then heat under reflux. Okay, so heat under reflux. Okay, next we have exercise 4.4. Reaction scheme below shows how compound C can be made from malonic acid. So malonic acid is given on the left. Okay, and then C is made from B via intramolecular esterification. Okay, so this is an intramolecular esterification. It's interesting. Yeah, so before we work on this question, maybe shall we try to calculate the degree of unsaturation for C? Yeah, so the degree of unsaturation for C will be 2n plus 2, so that will be 8 minus 4 divided by 2. So it has 2 degrees of unsaturation. And then you know that C is an ester. Yeah, so if C is an ester, so that contribute 1 degree of unsaturation because an ester contains a C-O. What about the remaining degree of unsaturation? Because you were told that C is made from B via intramolecular esterification, right? That means B has both a carboxylic acid and an alcohol. Yeah, so therefore C must be a cyclic ester. Yeah, so the remaining degree of unsaturation tells you that C is a cyclic molecule. So it's a cyclic system. Yeah, so basically we're just going to draw a 3-carbon ester. So I'm just going to draw a double bond O, and then O here, and then like this. That's it. And then since we know this, we are able to draw B out. So if you number this carbon 1, 2, 3, yeah, so that will be 3, 2, 1 carboxylic acids. Okay, so B will look like this. Okay, so it's an intramolecular esterification. And then the first step involves lithium aluminum hydride in dry ether, 1 equivalent. What's the meaning of 1 equivalent? That means that one of the carboxylic acid gets reduced. It can be any of them. Yeah. Or it can be both. But if it's both, then B is not formed in significant amounts. Or if it's both, then you'll be one of the byproducts. Sorry, not byproduct, the side products. Yeah. So therefore, intramolecular esterification is not likely to take place. Okay, so it's only when I have a carboxylic acid and the alcohol group that intramolecular esterification can take place, like the way we do it. Okay, so so you notice that if we are using degree of unsaturation well, if we use it well, we are able to get a lot of clues from it, and that's actually helped us drastically in problem solving. Okay, so that's the end of exercise 4.4. Next, we'll be looking at section 5 on carboxylic acid derivatives. So what are carboxylic acid derivatives? Basically is any compounds made from carboxylic acids. Yep, so if you recall, for carboxylic acids, this portion is an OH. So after the OH is being replaced by groups such as Cl, then the compound will be called acyl chloride. If it's replaced by OR, then you'll be called an ester. Yeah, so OR prime essentially is an alkoxy group. Yeah, so this is an alkoxy group if you want to be strict about terminology. Then NH2 is an amide. So you can have an amide or even a primary amide, NHR, or even a secondary amide, NR2. Okay, and it can also condense with another carboxylic acid to give you something known as acid anhydride. Yeah, so this is the anhydride functional group, but it's not in your H2 curriculum, so you don't really need to know. But sometimes in exams, will tend to test you on, or you get to see anhydride appearing occasionally. Okay, for the topic on carboxylic acids and its derivatives, we will not be covering amides because amides will be covered under topic 19 on nitrogen compounds. Okay, so we'll straight away move on to 5.2 on nomenclature. Yep, so over here we are looking at two functional group, acyl chloride and ester. Yep, so for acyl chloride, we basically just replace the term oic acid with OL chloride. Yeah, so pentanol chloride is derived from pentanoic acid. Then 3-ethyl hexanoyl chloride is derived from 3-ethyl hexanoic acid, etc., etc. And then for ester, the parent's name will come out later. Okay, so so if you take a look at this, maybe let me color code in yellow. So over here, this particular portion. So this is the parent. So the parent is 3-methylbutanoate. Okay, then the group which came from alcohols, in this case it's the methyl group, so we'll put the name in front. So this compound is this particular ester is known as methyl 3-methylbutanoate. Okay, so let's try again. So over here we have the carboxylic acid over here. Okay, so this is the carboxylic acid, so this is the ethanoic. Okay, then the phenol, which contributes the nucleophile. Okay, we'll put the phenol in front. Okay, so maybe earlier on when I color code, I should also color code the O over here, yeah, to make it more accurate. Okay, and then methyl benzoates. Okay, so the methyl group came from the alcohol, so again the OCH3. Yeah, okay, and then it's a derivative from benzoic acids. Okay, so that's about it. And usually for esters, we have to be a little bit clear how we write the formula. Yeah, so for example, if methyl benzoate, it's written this way. So maybe just let me show you. Okay, so there is a difference between something like this, okay, versus let's say something like this. So do not write it the reverse. If you write it the reverse, it means different things. Yeah, so for the first one is the ester of benzoic acid. For the second one is the ester of ethanoic acids. Okay, so that's the difference. So the acidic portion is over here. So I think I mentioned, so this is a benzoic acid, and then you use methanol to condense together to form this particular ester. And then for the other case here, I'm using phenol together with ethanol chloride. Of course, we can't use ethanoic acid because, as you learned earlier on, phenol is not a very good nucleophile, so we have to convert phenol to phenoxide, and then of course we can't use carboxylic acid, we have to use ethanol chlorides. Right? Okay, so we'll move on to the physical property of carboxylic acid derivatives. Yeah, so for example, the derivative of ethanoic acid, so we have ethanol chloride with an MRAL 78.5, methyl ethanoate MRAL 74, they are quite close. You notice that their boiling point is lower than that of ethanoic acids. I think for a very obvious reason, because ethanol chloride and methyl ethanoate, they can't form hydrogen bonds with each other. Yep. So in that sense, ethanoic acid being able to form hydrogen bonds and with a MR relatively close to the other two, the strength of the hydrogen bond is still more significant as compared to the other two, where they exhibit intermolecular dipole, or intermolecular permanent dipole interaction or attractions. Okay. Yep. Then if you look at solubility, esters are very, very much less soluble in water as compared to carboxylic acid and alcohols. The obvious reason is it's not capable of forming very significant hydrogen bonds with water. Yeah, you may argue that for an ester, right? So for example, let's say ethyl ethanoate. This is a very common ester, always being used as solvents. The short form is called EA, ethyl acetate. Yeah, you may argue that the lone pairs of electrons here on the oxygen can form some extent of hydrogen bonds with water, but it's really quite insignificant because of the alkyl chain. Yeah, so the alkyl chain, to some extent, they form pretty strong dispersion forces between the molecules as well as the PD-PD. So that's why the hydrogen bonds form is not very significant, and esters are really quite insoluble in water. Okay, so ethyl acetates, it's already the slightly more soluble ones compared to the rest lah. Yeah, it's more soluble than the rest of the esters. Acyl chloride, you can't discuss its solubility in water because immediately it will hydrolyze in water. Okay, so I think this is something you need to remember. Not remember lah. I think if you look at this particular group, you know that it doesn't look very stable. So immediately the water nucleophile replaces Cl, and in the process it gives you hydrochloric acid, which is a strong acid. Okay, so acyl chloride completely hydrolyzed in water. I think this is something you need to be aware of lah. Okay, acyl chloride colorless liquids are strong irritating odor, sharp irritating odor, because once you open up a bottle, it will immediately hydrolyze with the moisture in the atmosphere to give you hydrogen chloride gas. I'm going to show you a video of how acyl chloride will hydrolyze. Yep, so just bear with me for a while. Okay, so this is the video.
Ethanoyl chloride is a colourless reactive liquid which fumes in moist air.
Okay, you can see the fuming is hydrogen chloride.
The reaction with warm water was violent. Large volumes of choking fumes were formed, which gave a dense white smoke with ammonia gas. The reaction with ethanol was also violent.
Okay, take note of the white fumes being produced. Okay, I think I'll just stop here. You can watch the video on your own if you wish to. Just Google or go to YouTube and find out ethanol chloride reactions. Okay, so now I will go back to our lecture examples. Okay, so esters are colorless liquids with a pleasant sweet fruity smell. Not often sweet smelling. Sometimes it can smell like nail polish removal. Yeah, so so it's not often sweet smelling, but usually if you're asked in the lab to describe the smell, if you try to smell it, yeah, it has a bit of a sweet or disgusting nail polish removal kind of smell. So maybe in one of the labs, when you produce an ester, you can try smelling it and tell me what it smells like. Okay, with that, we'll move on to exercise 5.1. Suggest a reason why the boiling point of ethanol chloride is higher than 2-chloropropane. Okay, so I don't think this is a very difficult question to answer. I think the first thing is first of all, we need to compare. So ethanol chlorides, okay, versus 2-chloropropane. Okay, if you take a look at if you just simply calculate the MR, we have a methyl group here, which is 15, and then a CO 16 plus 12, that's 28, and then with Cl, that's 35.5. Yeah, if you add them up together, that's 18.5, 3, 4, 5, 6, 7, 78.5. 2-chloropropane will simply be 15, 30, 14, and 35.5. So that's 65.5, 79.5. So they have relatively similar relative molecular mass. Yeah, but the boiling point of ethanol chloride is higher. I think we can understand it by knowing that the C double bond O is a highly electron withdrawing group. Of course, there's a very huge dipole moment towards the oxygen, delta plus, delta minus, and of course you have a delta minus here. Yeah, so this very strong dipole, right, will give rise to a very strong permanent dipole interaction between ethanol chloride molecules, yeah, as compared to that between 2-chloropropane molecules. Yeah, so I would expect 2-chloropropane molecules to have slightly weaker PD-PD attractions as compared to that between ethanol chloride. So because I need more energy to overcome the stronger permanent dipole interaction between ethanol chloride molecules, then I expect a higher boiling point. Okay, yep, so that's a very simple chemical bonding kind of explanation, which I would expect all of you to be able to explain it now. Then moving on to exercise 5.2, which of the following statements best explains why the solubility of ethyl ethanoate, this is the ethyl acetate I was telling you about, EA, in water is lower than that of propanoic acid. So again, I already make my points pretty clear. Propanoic acid forms quite extensive hydrogen bonds with water. Okay, then ethyl ethanoate probably can't form very strong hydrogen bonds. Okay, so if you look at option A, ethyl ethanoate molecules cannot, so the word is cannot. Actually it can, right? I think I mentioned to you earlier on. Because of the lone pairs of electrons here, so potentially it can form hydrogen bonds, but it's likely to be weaker. Okay, so so cannot is incorrect. Ethyl ethanoate has a larger non-polar chain, or this is nonsense because focus here is on hydrogen bonding. Okay, option C, you notice that it resonates quite well with what we have been talking about. Ethyl ethanoate molecules forms weaker hydrogen bonds as compared to that between propanoic acid molecules. So I think this makes perfect sense. So I will choose option C. But before that, let us take a look at option D. Ethyl ethanoate molecule has a greater number of electrons. Yeah, so again, I don't think this is a key reason. If you look at their relative molecular mass is about the same. Yeah, it's only, I mean, the numbers only matter if it's like, say 10 times greater, or let's say 8 times greater. But if it's like just 10, 20 ml greater, or 10, 20 units greater, I think that is not a major issue. Okay, then next we are going to move on to the chemical reactivity of carboxylic acid derivatives. Yeah, so this can be seen as a relatively important section. It's good for the students to know, so it's good for you guys to know. But if you are taking H2, then I think it will be sufficient for you to understand that acyl chloride is the most reactive out of all the carboxylic acid derivative lah. And then amides is the least reactive. Yeah. If you truly want to understand why, then I think you have to read up a little bit more beyond the H2 curriculum. For example, read up on some introductory organic chem textbook used by freshmen. Yeah, it will help a lot. But I can roughly give you a reason. Just give you I won't say I wouldn't say it's a simplistic reason, but I will just explain in a very simple way why is it that acyl chloride is the most reactive as compared to the rest, and then why is amide the least reactive, and then the two in the middle. I will also attempt to explain it, and hopefully after explaining it, it does make a little bit of sense to many of you. Okay, I think first of all, right, when we look at all the carboxylic acid derivatives as well as carboxylic acid itself, right, we want to focus on the heteroatom directly bonded to the carbonyl carbon. Okay, so I'm going to highlight in pink over here. So for acyl chloride, that will be Cl. For carboxylic acid, it will be oxygen. For ester, it will be oxygen as well. And for amide, it will be nitrogen. Okay, so that's the number one thing we want to focus on. And then the second thing we might want to ask ourselves would be which period does this heteroatom belong to? Yeah, so for chlorine, it's in period 3. Okay, period 3. For the rest is period 2. Okay, period 2, period 2, period 2. Okay, so that means that in terms of orbital size, the valence orbital size, right? I would expect the oxygen and nitrogen, right? In the presence of lone pairs, because if you take a look at the individual structures, you know that the nitrogen and the oxygen, the nitrogen has one lone pair, the oxygen actually has two lone pairs, but only one of it is largely residing in the p orbital. Okay, so it has a lone pair here, and of course the chlorine has a lone pair here. Okay, so what if the lone pairs of electron is present? Okay, so we can understand this by knowing that the lone pairs of electrons will delocalize into the carbonyl oxygen because the CO pi bond forms a pi bond, obviously. So the p orbital being parallel to the CO pi system, it should be able to delocalize into the pi system. Yeah. However, right, if you look at chlorine, right, there is an orbital mismatch. Okay, so what do we mean by orbital mismatch? So orbital mismatch comes in terms of the size lah. So for example, CO, right, maybe, or rather it's using the 2p orbitals. Yeah, but for Cl, Cl is using 3p. So this is 3p and this is 2p. So I would not expect the overlap between a 2p orbital and a 3p orbital to be that good. So we call this an orbital mismatch. Yeah, so in that sense, the extent of delocalization of the lone pairs of electrons on Cl into the CO pi system is kept at a minimal. What does this mean? This means that the electron density, or rather the electron deficiency at the carbonyl carbon is the greatest at the carbonyl carbon at the acyl chlorides. Yeah, so why is this electron deficiency the greatest? Because, right, the CO and the CCl, right, is able to exert an electron withdrawing inductive effect on the carbon. Okay, the oxygen exert both inductive and resonance effect, of course, because the pi electron cloud is displaced towards the oxygen. Yeah, and you might expect the lone pairs of electrons on Cl to also be delocalized over, but that is not the case because of orbital mismatch. Yeah, so because of orbital mismatch, therefore the Cl only exert an electron withdrawing inductive effect on the carbon. Yeah, so I have an inductive withdrawing effect towards the O, I have an inductive withdrawing effect towards the Cl. Yeah, that makes the carbonyl carbon in acyl chloride highly electron deficient. So it's being highly electron deficient, therefore it is highly susceptible to nucleophilic attack. Yeah, so therefore acyl chloride is the most reactive amongst all. Okay, yeah, so I think we have cleared the acyl chloride. Now we'll attempt to look at carboxylic acid, esters, and amides. Yeah, so for carboxylic acids, esters and amide, the hydrogen atom, in this case oxygen and nitrogen, the lone pairs of electrons on them, right, is in the 2p orbital. So in that sense, that is the orbital matches that of the CO pi system. Yeah, so I would expect quite a large extent of delocalization of the lone pairs of electrons towards the carbonyl oxygen for all the three systems. Yeah, however, I expect the extent of delocalization for amides to be the greatest. Okay, so so this lone pair of electrons, the extent of the localization of this lone pair of electron to the carbonyl oxygen is the greatest. Yeah, why is it the greatest? Because nitrogen is less electronegative than oxygen. Yeah, so nitrogen being less electronegative than oxygen, right, it is not able to hold on to its lone pairs of electrons as strongly as the other two oxygen in ester and carboxylic acids. When I mean the oxygen bonded to the R prime and the H. Okay, not the carbonyl oxygen, obviously. Yeah, so because of that, the extent of delocalization of the lone pairs of electrons on the nitrogen in amide towards the carbonyl oxygen is the greatest. Yeah, so when the extent of delocalization is the greatest, that makes the carbonyl carbon over here significantly electron deficient as compared to the other two carboxylic acids and esters lah. Okay, so because the electron deficiency of the carbonyl carbon in amide is the least, so it is the least susceptible to nucleophilic attack, therefore the least reactive. Okay, yeah, so in general for H2, it is sufficient enough for you guys to know why is amide the least reactive and why is acyl chloride the most reactive. Okay, then in that sense, you might also be wondering, what about esters and carboxylic acid? How can we explain the difference lah? Okay, so we can understand the difference between esters and carboxylic acid simply by looking at the fact that the alkyl group, okay, what is the meaning of the alkyl group? So this is the alkyl group over here, the R prime, sorry. This R prime, right? Alkyl groups are electron donating. So the electron donating alkyl groups enhances the electron density at the oxygen. Yeah. So therefore the lone pair electron density at the oxygen in ester is slightly more enhanced. So that means that the delocalization of the lone pairs of electrons in the ester over to the carbonyl oxygen is slightly greater as compared to that of carboxylic acid. So therefore the carbonyl carbon of ester is less electron deficient as compared to that in carboxylic acid. So that makes ester less reactive as compared to carboxylic acid, but more reactive as compared to amides. Yeah, then some of you will ask, but oxygen and nitrogen are more electronegative than chlorine. What about the sigma withdrawing effect? Okay, so remember what we discussed earlier on. If there are two opposing effects, sigma and pi, right? When pi effect is the dominating one, the pi effect will usually override the sigma withdrawing effect. Yeah, so the pi effect dominates lah. Okay, so there are some explanation given here. You may read through, but if you can understand what I'm trying to explain earlier on regarding the orbital mismatch of chlorine, why is it that the lone pairs of electrons on the chlorine in acyl chloride cannot be delocalized, and why is it that the sigma withdrawing effect dominates, etc. If you can understand everything, I think you might not need to look through these two reasons, because these two reasonings are a little bit shortened, maybe not as detailed as what I've covered, but if not, I think you can simply just understand it or try to remember the trend by knowing that acyl chloride is the most reactive, amide is the least reactive. I think that will be sufficient. Okay, so with that, I'm going to move on to section 6 on acyl chloride. Okay, so for acyl chloride, we have the preparation of acyl chloride, which we already covered in section 4.2.2 under nucleophilic substitution of carboxylic acid. So we replace the OH with chloride using three reagents. I think we talked about them: PCl5, PCl3, and SOCl2, thionyl chloride. Okay, and then the reaction of acyl chloride, hydrolysis to give you carboxylic acid. So basically, you have seen from the earlier videos, when I expose acyl chloride to water, it will simply just fume in the air, and there's white fumes of HCl. I hope you have seen it earlier on. So the white fumes is quite obvious. Okay, so the reaction can be quite violent, depending on the temperature. So you have to take note of it, and safety is of utmost importance. Okay, for exercise 6.1, if you are being asked to design a simple chemical test to distinguish between carboxylic acids, ethanoic acid, and acyl chloride, I think what you can do is simply use what we discussed earlier on. You can just add a few drops of water. Okay, so I can add maybe one of the tests you can use. Let me just right here. Add a few drops of water to the unknown. Okay. So for ethanoic acid, it will simply be miscible, but for ethanol chloride, you are going to observe white fumes of HCl. Yeah. Another way you can go about doing things is simply to add silver nitrate. Yeah, because silver nitrate contains water, so there's an aqueous here. So basically, when you add silver nitrate in, ethanol chloride will be hydrolyzed completely to give you the free chloride, and the presence of the free chloride will result in the ionic products exceeding the KSP, so you will get white PPT of silver chlorides. Okay, so that is another way you can distinguish between acyl chlorides and ethanoic acids, or carboxylic acid in general. Okay, then for 6.2.2, condensation to form ester. So as we mentioned earlier on, for carboxylic acid, you need corn sulfuric acid as the catalyst. Yep, but for acyl chloride, you do not need corn sulfuric acid, so it will simply just react quite readily because the carbonyl-carbon of acyl chloride is highly electron deficient, as what we explained to you earlier on. So therefore highly susceptible to nucleophilic attack even by a weak nucleophile. Okay, next we are going to look at exercise 6.2. We are being asked what are the starting materials for the preparation of phenol benzoate. So I think we have to draw it out. Phenol benzoate is the ester of benzoic acids. Okay, and very clearly we also use phenol. Yeah, so we know that if we use phenol, we can't simply just react with carboxylic acid. We need to react with the acyl chloride version of the carboxylic acid. Yeah, so very clearly, the only option here we have is benzoyl chloride. Yeah, so out of A, B, C, D, only option D gives us benzoyl chloride. So I think only D is the answer. Yeah, but what about phenol? Yeah, so D contains phenol here. So again, this is okay. And what is the role of sodium hydroxide? The role of sodium hydroxide is to deprotonate phenol. Okay, so please do not be mistaken by the comma over here. Yeah, do take note that what you need to do here is you need to add sodium hydroxide, preferably solid sodium hydroxide, to phenol. And for these two, right, you will result in the deprotonation of phenol to give you phenoxide and ion. Yeah, which is a stronger nucleophile than phenol. Yeah, so only after you form phenoxide, then you can introduce benzoyl chloride. Yeah, so because I have a stronger nucleophile, so I expect the reaction between phenoxide and benzoyl chloride to be faster, and that's how I'm going to end up with my compound known as, my product known as phenol benzoates. Okay, so I hope you find exercise 6.2 quite okay to work on. I think the choices are quite obvious as well. Okay, so do not expect such straightforward questions for your exams. Okay, then next we'll move on to exercise 6.3. The small beehive beetle, which invades colonies of the honeybee, identifies these colonies by detecting the bee's own alarm signal, the pheromone 3-methyl-butyl ethanoate. Okay, so first of all, right, we need to be able to draw out this particular compound, because if we can't draw it out, then I think there's no point in doing the question. Okay, so this ester is the ester of ethanoic acid. Okay, so let me draw the ethanoic acid first. Okay, sorry, yeah. Okay, sorry, just let me draw it out. Okay, so this is the ethanoic. Okay, and so let me try to draw the alcohols. Okay, so it's like this. O, so O is here. Okay, and it's actually a butanol with a methyl group at the third carbon. Okay, so we are going to have 1, 2, 3. Sorry, 1, 2, 3, and 4. Okay, so there's a methyl group over here. Yep. Okay, so this is 1, 2, 3, 4. So the third carbon has a methyl group. Okay, so what I've drawn above is 3-methyl-butyl ethanoate. Yeah. So if we look at the whole list, I think we have to be very clear. We need to use ethanoic acid or ethanol chloride. Okay, so we have ethanol chloride here, ethanol chloride here. So the answer is either option C or D. Okay, I hope you understand why we can't use the other way around. I have already explained to you earlier on in terms of the naming. Yeah, because when it ends with blah blah OH, that means that is the carboxylic acid which we should be using. Okay, then after that we are just going to fit in everything lah. And then if you try to fit in, this is carbon number 1, carbon number 2, carbon number 3, and then this is carbon number 4 and 5. Okay, so C seems to be the answer. For donkey, it's not the answer because it does not correspond to the alcohol 2-methyl-butyl 1-or. It doesn't correspond to that. Yeah, so I will only choose option C as the answer. Okay, next, section 6.2.3, condensation to form amides. Okay, so this is also nucleophilic acyl substitution. Yeah, so acyl chloride reacts readily with ammonia to form amides, and then primary and secondary amines to form N-substituted amides. Okay, so basically the HCl comes from the Cl here and one of the H over here. Okay, the Cl here and one of the H, and then the Cl here and one of the H. Okay, so I think observation will be white fumes of HCl evolved. Okay, tertiary amines can't react because there is no H being evolved. Okay, then ammonia and amines are either in excess to ensure that the reaction is completed, and at the same time it helps to remove the acidic hydrogen chloride gas. Okay, via this acid-base neutralization reaction to form ammonium chlorides. Yep, carboxylic acid cannot be used. Okay, so this is very important and often is being asked in exam to trick the students. The reason is carboxylic acid and amines react via acid-base reaction instead. Yeah, so do remember that if you want to form amides, the first thing you need to do is to convert the carboxylic acid to acyl chloride before you react with the relevant ammonia or amines. Okay, if you just react them straight away, please expect acid-base reaction to take place instead. Next, we have exercise 6.4. Yep, we are being asked which of the following compounds or which of these compounds cannot be made in one step from ethanol chlorides. Right, so if you take a look at A, right, it's quite a trick question. This is actually a ketone. If you stare at it carefully. Yep, it's actually a ketone. It's not an ester because sometimes if you stare wrongly or you stare incorrectly, you thought it's an ester. Yeah, so it's actually a ketone. And you probably recognize that you do not know of any reaction which gives you a ketone from ethanol chloride in one step. Okay, so therefore option A is the option which I will pick as the incorrect response, or rather the correct response to this question, because butanone cannot be made using one step from ethanol chloride. Okay, can we make this amide? Yes, we can. Ethanol chloride with phenolamine. Can we make this amide? Yes, we can. Ethanol, chloride, and ammonia gas. Can we make carboxylic acid? Yes, we can. We can just hydrolyze ethanol chloride, and it will give us the carboxylic acid. Okay, yeah. Then 6.3 over here, we have the relative rates of hydrolysis of acyl chlorides, alkyl chloride, and aryl chloride. I think earlier on in the introduction, I give you the last learning objective, and I mentioned that very often in exams they like to test this because it's probably one of the few recall questions which does require some degree of understanding. Yeah, and as I mentioned earlier on, acyl chloride is the most reactive, and I think we can understand why, because of the sigma withdrawing effect of both oxygen and Cl, and the lack of lone pairs of electrons on chlorine delocalizes over to the carbonyl group. Yeah, so because of that, the carbonyl carbon in acyl chloride is highly electron deficient, so therefore highly susceptible to nucleophilic attack. Okay, in our case, highly susceptible to hydrolysis. Yeah. Okay, so I think the reasoning is given here. That's the electronic reasoning. So there are two reasonings usually we will give, electronic and steric. But usually electronic reasoning dominates over steric. Okay, so in this case, in terms of steric reasoning, we are just saying that the acyl chloride is trigonal planar in terms of geometry about the carbonyl carbon, so therefore more susceptible to nucleophilic attack. Okay, then for chloroethane, there is only one inductively withdrawing chloro group. Yeah, so although the carbon directly bonded to the chlorine is electron deficient and probably susceptible to nucleophilic attack, but it can't be carried out in room temperature because the reaction will be too slow, so it needs to be heated under reflux, or at least elevate the temperature so as to increase the rate of reaction. Yeah, we can simply compare between ethanol chlorides and chloroethane by simply focusing on the fact that the carbonyl carbon in ethanol chloride is significantly more electron deficient as compared to the sp3 hybridized carbon bonded to the Cl in chloroethane, and therefore more susceptible to be attacked by water in hydrolysis reaction. Okay, for chlorobenzene, we have discussed quite a bit in our aryl halogenoarenes portion in halogen derivative. Okay, so over here we say that the lone pairs of electrons on chlorine is partially delocalized into the phenol pi system, so it gives the CCl bond a partial double bond character. Yeah, and because of this, it makes the carbon bonded to the Cl resistance to nucleophilic attack, and the CCl bond cannot be broken that easily. Okay, so based on steric reasoning, you can also argue that the aromatic ring hinders the attack by the nucleophile. Okay, and of course the electron-rich pi system of the phenol ring will repel incoming nucleophiles, such as water. So it's therefore not susceptible to hydrolysis at all. Okay, then what about reaction with silver nitrate? As we mentioned earlier on, for acyl chloride, once I add in drop-wise of silver nitrate, hydrolysis will take place immediately, and free chloride is present or will be produced, and because of that, the ionic products of silver chloride will exceed its KSP, so immediately I will observe precipitation of silver chloride. Okay, but for chloroethane, not so straightforward. There is a need for us to heat it with sodium hydroxide in order to expel the chloro group out. Yeah, even if we do not heat it with sodium hydroxide, we need to use a slightly harsher condition such as ethanoic silver nitrate, which means I'm going to dissolve my organic compound in ethanol, and then inside the ethanol I'm going to put in silver nitrate salts. Yeah, so this will help in the hydrolysis of the CCl bond. And then for the chlorobenzene, no precipitate observed even after prolonged heating. Okay, yep. We're gonna do exercise 6.5. There are two questions. Okay, so liquid L gives white PPT only when shaken for some time with aqueous silver nitrate which of the following structure is likely to be L. So definitely, let me see, only when shaken with silver nitrate. Yeah, so definitely not chlorine bonded to the phenol ring, and definitely not these two. Okay, so I'm only looking at L here. Okay, over here. I think that's quite straightforward, as in because there's no heat, no sodium hydroxide involved, so I will only be picking acyl chlorides. Okay, then for question 2, which hydrolysis reaction using sodium hydroxide will be the slowest? We are looking at hydrolysis. Okay, will be the slowest. Okay, so in this case, I'm not going to choose acyl chlorides. I'm not going to choose my primary chloroalkanes over here. I'm definitely going to choose chlorobenzene. Yeah, because it might not even take place. Yeah, so it will be damn slow unless I carry out under very harsh conditions such as high pressure, high temperature. Yeah, so the product is likely to be this. Yeah, so anyway, I'm going to choose donkey, or option D. Okay, yeah, so with that, I think we can move on to the next portion on esters. Okay, so I'm going to have an introduction here. Esters are generally sweet-smelling compounds, widely used as flavorings. Okay, so the linkages occurs naturally in fats and lipids. I'm not going to go through a lot of introduction here. Yeah, so there are some sweet-smelling esters such as strawberry, and then you have a banana, one with a banana smell. Isoamyl acetates, and then methyl butanoate is responsible for the smell of apples. Okay, fats are made of triglycerides, which are esters of fatty acids. Okay, so there was a database question being set, I think 2015 A levels. Okay, so I think you can look forward to that. And then esters are prepared industrially, mainly for the use of as accents, perfumes, artificial flavorings, or as organic solvents such as ethyl acetates or ethyl ethanoics. Okay, so it smells like nail polish remover. Okay, I mean that's why it's put as varnishes here. Okay, and then yeah, that's about it. For isomerism, its direct isomer will be the equivalent carboxylic acid. We can understand why, because for the same molecular formula, both of them have degree of unsaturation of 1. Yeah, so therefore an isomer of carboxylic acid is likely to be an ester. Okay, of course you can have chain isomerization, etc. But I think the main thing we want to look at is if we want an isomer with a different functional group, then we are really looking at esters and carboxylic acids. Okay, or I can also change the position. I can use different carboxylic acid to make the esters, or different alcohols to make the esters as well. Okay, then we have exercise 7.1, when we are supposed to draw the structure of 4 isomeric esters with this particular formula, C4H8O2. Okay, and we are supposed to name them. Okay, so we'll just begin with the longest chain, but when you begin with the longest chain, then please take note that it should not be butanoic acid, because butanoic acid you can't have esters anymore, because that is really the functional group isomer of the ester. Okay, so I will have to start off with propanoic acids. Okay, so I'm going to start off with propanoic acid over here. So this is propanoic acids. Okay, so OCH3. Yeah, because it is the ester of propanoic acid, so I will name it as methyl. Okay, propanoids. Okay, and then another thing we can do is we can just swap. We can just swap these two groups. Okay, I just insert it inside here. Okay, so I'm going to end up with something like this. Okay, I mean, it's not literally an insertion. Okay, I'm just shifting a CH2 over. Okay, so I'm going to have O, CH2, CH3. Yeah, so this is our famous ethyl acetate or ethyl ethanoic. Okay, and then we can do some more. We can again swap this group in and then leave the H behind into here. Okay, so what we're going to end up with is the ester of methanoic acids. Okay, CH2, CH2, CH3. Okay, so that will be 1 propyl, okay, methanoic. Why is it 1 propyl? Because the original hydroxy group is in the first position. And you notice that this portion we can have a position isomerism here. Okay, so what we're going to do is I'm just going to swap the groups around. Maybe I'm just going to swap the H with the CH3 around. Okay, so I'm going to end up with methanoic. Okay, and then I have a C, H here, CH3 and CH3. Okay, so with this is 2 propyl, okay, methanoic. Alright. Okay, so these are the 4 esters with the molecular formula C4H8O2, and we have successfully named them. Okay, and then preparation of esters can be prepared from condensation reactions between carboxylic acid and alcohol, which we discussed earlier on, using corn sulfuric acid as the catalyst, or condensation reaction between acyl chloride and alcohol. Okay, so we have exercise 7.2. Which procedure gives the best yield of ethyl ethanoate starting from ethanoic acid and ethanol? Okay, so they want the best yield. So definitely I'm going to make ethanoic acid. I'm going to elevate the reactivity of ethanoic acid by converting it into an acyl chloride. Okay, so option A seems to work. And then after I add ethanol to the acyl chloride. Yep. Option B will not work. Option C will not work as well, because sodium hydroxide and ethanoic acid, you are going to form ethanoic anion, which is the conjugate base of ethanoic acid. And the ethanoic anion is actually more electron rich as compared to ethanoic acid. So it is susceptible to further nucleophilic attack because it will repel away the incoming nucleophile. So C is gone. D, refluxing ethanol with concentrated H2SO4. This probably work as well, but it's not going to give you a very high yield. Yeah, because anything involving carboxylic acid, alcohols, and corn sulfuric acid, it tends to be more of an equilibrium reaction. Okay, so maybe I will give option D a miss. Okay, so option A will be the best option for me to produce the ester. Okay, ethyl ethanoate. Okay, so with that, we're going to look at reaction of esters. Okay, so you would be familiar with acid and base hydrolysis. Basically, acidic hydrolysis, you use dilute sulfuric acids, and then you heat under reflux. Okay, and then your byproduct is the alcohols, and then of course what you're going to end up with is the carboxylic acid, the relevant carboxylic acid. Acid hydrolysis tends to be reversible, so we tend to use a large volume of water to ensure that the position of equilibrium lies all the way to the right. Okay, so if we want to produce alcohols and carboxylic acids, then we will use minimal amount of water. So we tend to catalyze the reaction using concentrated sulfuric acids. Okay. Base hydrolysis usually give you a very high yield because, as we mentioned earlier on, once the carboxylic anion is being formed, its resistance to further reaction. So this cannot go back to the left. Yeah. So once I form the carboxylic salt, in most cases, right, I can usually separate it from the alcohol by simply adding sulfuric acid, and your carboxylic acid will precipitate out as the insoluble carboxylic acid. Yeah. Why is it what you might ask, why carboxylic acid is insoluble? Usually, if the alkyl chain is quite long, as we mentioned earlier on, it will be quite insoluble in water. Yeah. So when we form carboxylic salts, the carboxylic salt is very soluble in water because of the ion dipole interaction it forms. But if you want to just filter out the carboxylic acid, then you need to add you need to add sulfuric acid to it, so that it will just come out as a PPT. Okay, yeah. So I think it's mentioned over here. Base hydrolysis is rapid and irreversible. acid hydrolysis is reversible. Yeah, so if you want to perform an irreversible reaction, then I think it's good to do basic hydrolysis. Yeah, okay, so I think I mentioned this as well. To obtain the carboxylic acid, aqueous acid is added to protonate the carboxylate anion. In the process, you will form the PPT. Okay, the PPT is color depending on the R group as well. Okay, then I think finally we have exercise 7.3. Draw the structures of the products formed when the following ester is subjected to acidic hydrolysis. Okay, so acidic hydrolysis, I'm going to cleave this portion. Okay, so I'm going to end up with the corresponding carboxylic acids like this. Okay, as well as the alcohol, which is like this. Okay, that's a CH H here, the Br and the CH3. Okay, so the Br is here. Yeah, for base hydrolysis, because OH minus is also a nucleophile, so I expect nucleophilic substitution to take place on the Br. Okay, so I'm going to end up with the carboxylate salts plus HOC and then OH, CH3 and H. Okay, some of you will recognize that this compound is not very stable because the carbon is bonded to two OHs. Yeah, so if you are aware, this compound will quickly lose the water to give you the corresponding aldehydes. So you get plus H2O, and then I'm going to get ethanol like this. Okay, something along this line. Yeah, but of course, if you are not sure, not sure in the sense, this is actually not in the H2 curriculum. So you can just ignore what I've written in pink and then just write your answer as this. I think that would be okay. Right, okay, then I think we have come to the end of the lecture notes. The last bit is the summary of reaction involving carboxylic acids and their derivatives. So I will leave it to you to write down the summary and just jot down the answers to 1, 2, 3, 4, 5, 6 all the way to 11, as well as the reaction involving acyl chloride. Okay, so do spend a bit of time writing out this particular summary because it contains most of the reaction you need to be aware of for this particular chapter. Okay, so with that, we have come to the end of the lecture. So the final lecture on organic chem will be nitrogen compounds. That will be topic 19.